Good morning, students. Today's class we are going to learn about electrostatic potential energy. As you could see in the picture, there's a charge Q plus Q which is placed at the origin, and you could also see another charge Q prime which is a test charge placed at a point R. You could also see another point P on the same line. Now, if I am going to bring the test charge Q prime from the point R to the point P, that is towards a positive Q charge. So, when I bring two positive charges closer to each other, there's a force of repulsion. So, we need to do some work to overcome this force of repulsion, and this work done is stored as potential energy or electrostatic potential energy. Since Q and Q prime, as I already said, both are positive. So, there's a Coulomb repulsive force, and this Coulomb repulsive force is acting along PR. You could see in the picture again, charge Q and Q prime are positive. So there's a force of repulsion. So they tend to move away from each other. So this force is acting along PR. But I am giving some external force in order to overcome this force of repulsion. So the external force what I am applying is along RP. So you could see two forces here. One is a force of repulsion acting along PR, and other force is my external force what I am applying to overcome this force of repulsion, that is along the direction RP. So I could say the external vector force F vector external is equal to minus F vector Coulomb, since both are equal and opposite. So earlier we have learned the formula for work done in 11th standard. General formula for work done is force into displacement. So I am writing a formula for work done here. W is equal to integral R to P F external vector dot dr vector. We know R is the starting point for the test charge Q prime, and P is a point where we have to move it. So that is the final point. So the external force what we are applying is F vector external, and dr vector is a small displacement of the test charge Q prime within the distance R to P. Like gravitational force, Coulomb force is also a conservative force. Earlier we have learned what is meant by conservative force. That is, the work done is independent of the path and it depends only on the initial and final positions of the test charge. Suppose if potential energy associated with Q prime at the point P is marked as UP, and the potential energy associated with Q prime at R is UR. Then difference in potential energy is defined as the work done to bring a test charge Q prime from a point R to P, and is given as UP minus UR. That is, difference in potential energy is nothing but the work done, or UP minus UR could be written as delta U. Delta U is nothing but difference in potential energy. So work done is equal to difference in potential energy, or in other terms, work done is nothing but the change in potential energy. So earlier we learned the formula W is equal to integral of R to P F external vector dot dr vector, and just now we learned the formula W is equal to delta U. So in the place of W, I could replace delta U in the formula. So my formula becomes delta U is equal to integral R to P F external vector dot dr vector. Further, we also know that external force and Coulomb force of repulsion are equal and opposite. So we have already come across this equation, that is F external vector is equal to minus F vector Coulomb. And in your previous classes, we have learned the formula for electric field. E is equal to F by Q, or F is equal to Q into E. So instead of writing minus F vector Coulomb, I could replace my F with the formula Q into E. So I could write minus Q prime E vector. Now, taking this equation, F vector is equal F minus F vector is equal to minus Q prime E vector, or F vector external is equal to minus Q prime E vector. I am just substituting the second formula into the first equation. That is, in the place of external F vector external, I am replacing with minus Q prime E vector. You could see the last equation, delta E U is equal to integral R to P minus Q prime E vector dot dr vector, or I could remove my Q prime vector out, Q prime outside. So my integral would be R to P minus E vector dot dr vector. So I get a final formula as delta U is equal to Q prime integral R to P minus E vector dot dr vector. So you know what is delta U? Delta U is nothing but difference in potential energy. Already we know this is nothing but W. So next slide, we'll move on to the next slide. Potential energy difference per unit charge is given by. So see the numerator of the formula, already we just derived delta U is equal to Q prime integral of R to P minus E vector dot dr vector. Now I am just substituting that here in this formula, delta U by Q prime. So numerator you have a formula of delta U, denominator you have Q prime. You could just cancel out Q prime of the numerator and denominator. So you are left out with the formula delta U by Q prime is equal to minus integral of R to P E vector dot dr vector. And an important note, the above equation is independent of Q prime. So the quantity delta U by Q prime could be written as minus integral R to P E vector dot dr vector is called the electric potential difference between the points P and R, and this could be written in terms of Vp minus Vr, which is nothing but difference in potential energy or potential energy difference delta V. The electric potential difference is defined as the work done by an external force to bring a unit positive charge from the point R to the point P. So here you have your formula of electric potential difference, that is Vp minus Vr. We already know Vp is electric potential at the point P and Vr is electric potential at the point R. So difference in this electric potential is called electric potential difference Vp minus Vr, or you could write it as delta V. So we already derived that delta V is nothing but minus integral of R to P E vector dot dr vector. Here, electric potential energy difference can be rewritten as delta U is equal to Q prime delta V. You may wonder from where you got this formula. Just have a look into it. We know that delta U by Q prime is equal to minus integral of R to P E vector dot dr vector. And in a second formula, we have said it's nothing but delta V. So I could write delta U by Q prime is equal to delta V. And next one, physically, potential difference. Difference means you need two places, 2 points. So physically, potential difference between 2 points is a meaningful quantity. But when I talk about the value of the potential itself at one point. If I just consider only one point, not 2 points, in that case, the value of the potential itself at one point is not meaningful. Therefore, the point R is taken at infinity and the potential is considered as 0. V infinity is equal to 0. Again, I'll repeat. The point R is taken at infinity and its potential is considered as 0. So, V infinity is equal to 0. So, I get a new formula for electric potential at a point P. So, electric potential at a point P is equal to the work done by an external force to bring a unit positive charge with constant velocity from infinity to the point P in the region of the external electric field. So, my formula becomes Vp is equal to, that is electric potential at a point P is equal to minus integral of infinity to P. Why? This because the starting point is infinity. From a very far point, we are just going to bring the test charge Q prime and we are just going to place it at the point P. So starting point is infinity and ending point is P. So integral of E vector dot dr vector. Here, you need to be very careful. We have learned two terms. One is electric potential difference and another one is electric potential. So, just let's pause ourselves to again learn what is electric potential difference and what is electric potential. Electric potential difference is nothing but is defined as a work done by an external force to bring unit positive charge from the point R to the point P towards the source charge Q. So, Vp minus Vr is equal to delta V, which is equal to integral of R to P minus E vector dot dr vector. Here we are considering the potential at 2 points Vp and Vr. And in electric potential, just when I say only electric potential at a point P, here it means that we are just going to bring a charge from infinity to the point P. So, my formula becomes Vp is equal to minus infinity to P E vector dot dr vector. We'll just learn some important points under this. Electric potential at a point P depends only on the electric field which is due to the source charge Q and not on the test charge Q prime. This is evident from the equation what we have derived. In your equation, both in Vp and delta V, your formula is independent of Q prime. It is dependent only on E vector, where E vector is nothing but the electric field which is due to the source charge Q. Second point, unit positive charge is brought from infinity to the point P with constant velocity because external agency should not impart any kinetic energy to the test charge. Some more important points. The unit of electric potential is joule per coulomb. The practical unit is volt, named after the scientist Alessandro Volta, who invented the electrical battery. The potential difference between 2 points is expressed in terms of voltage. So under this part, we have learned the formula of electric potential difference and the definition of electric potential difference. We have also learned the formula of electric potential and the definition of electric potential.